Okay, students, so today we are going to find shear force and moment diagram in order for you to draw the shear force and moment graph. Okay, this is actually this question is actually a question example in your slides which I have given to you. Okay, so this is the question in your slide for shear force and moment diagram of concentrated load. So the question in your slide says that you have a beam of A to D and two forces are load on the beam. There are two loads on the beam, 20 kilonewton which acted at A and 40 kilonewton which acted at C. So from A to B is 2.5 meter, from B to C is 3 meter, and from C to D is 2 meter, right? And it is being supported by one pin and one roller. Okay, one pin and a roller there. Okay, as you know, so if you remember the previous chapter that you learned about a reaction, you remember that if you have a fixed pin like this, wait, I have to check back in the chapter. I think was it chapter 3? I think it's chapter 3. Okay, yes, I have to refer back to chapter 3. You have gone through this with Dr. Dayang. Okay, if you have a pin, and also if you have a roller, so the reaction force will be if you convert this into free body diagram, you will have one arrow of force here and one arrow of force here. Okay, so now we want to continue to find the shear force and also moment diagram, as these internal forces is important when you want to design your beam. That's why we have to find the shear force and also bending moment in your beam, as the beam has been given load. Okay, let's transfer this into your free body diagram. This is your question. So I have transferred it into free body diagram. So when I transfer this to free body diagram, so this is how my free body diagram looks like. Okay, first step before you draw your shear force and bending moment diagram is actually to find the first step before you find shear force and bending moment diagram. What you have to do is you have to draw your free body diagram of your system given to you. So you have to draw your free body diagram. So the question just now, if you remember, you have one force and then one force at C, 40 kilonewton, and then the beam is 7.5 meter being split into A, B, C, D. So between A and B is 2.5. And then you have one pin here. So this pin is being represented by this arrow and this arrow. And then you have one force here at C, 40 kilonewton, one force at A, 20 kilonewton, and another roller here, which is also represented by one arrow of force. Okay, one arrow of force. So I would like to name this reaction force as this one RB and this one as RD. Okay. Now we have completed the first part of our shear and bending moment diagram, where we have drawn our free body diagram like this. Now, in order to find shear force and bending moment, the second step you have to do is you have to determine what is the unknown reaction force acting on the beam. Okay, before we continue with V and M, we have to find first the RB and also RT. Other forces acting on the system we already know, but we do not know what is RB and RD. So we have to do this calculation. So we have to use the equations of equilibrium. We have to use the equation of equilibrium. So I'll start. Normally I'll start with, because I have two unknowns. Okay, equations of equilibrium, how many components up to chapter 3? So you know you have summation of fx must be equal to 0. Summation of fy must be equal to 0. And remember in chapter reaction that you studied, moment and reaction with Dr. Dayang, you have encountered this summation of moment about a point here must be equal to 0 as well. So when you are doing shear force calculation, here shear force and bending moment calculation, you have to know that Fx will not be counted because we are not interested in Fx. So we are only interested with the transverse force, which the one that the one that vertical towards the beam. So that is what the force that is what required here. And we know that our reaction are also in y direction. Our reaction is in y direction. Fx will not be we are not interested in Fx direction of forces because we are not going to know about the moment, but what we want to know is about the RB and RD, which is actually perpendicular to the beam. Okay, right. And we also, since we have two unknowns, because in this system we have two unknowns, we have RB and RD, Fy, only Fy equilibrium is not enough, so we have to use moment equilibrium of moment to help us to get to solve these two unknowns, because we do not have Fx here. Okay, right. So now, normally for moment, normally I will start with moment. People will start with moment because if we start with moment, we definitely will cancel 1 point. So we will obtain one. We can easily determine one unknown. So in this case, I would like to determine RB using moment of equilibrium, moment equilibrium equation. I'm going to determine RB. So I'm going to do a summation of moment about D must be equal to 0. Okay, summation of moment D is equal to 0. So 0 is equivalent to, we have to pull all the forces to D. So we have forces 20 going this way. So we know that default system is plus this way, plus going counterclockwise if positive, as we learned from previous chapter. So we know this force going down and going this way, so it's going to have a positive moment. So I'm going to write down 20 kilonewton. Okay, how far is this point to D? This is 7.5. So times with 7.5 meter. Okay, and then we have RB. Okay, RB is going clockwise, so it's going to be negative plus negative, because it is summation, right? So but the sign for moment, the direction of moment in this case is negative. RB times by here to here is 5 meter. Okay, plus with, we have another force here, 40 force. This 40 is counterclockwise, that is positive. So positive 40 kilonewton times by 2 meter. By doing the calculation, and then you will get your RB equivalent to 46 kilonewton. Okay, so you solve for your RB. Once you get your RB, okay, now we use this equation to find RD. Okay, we know summation of default is going up is positive, summation of Fy equals to 0. So 0 is equivalent to 20, going down is negative 20 kilonewton, plus Rb going up is positive, minus 40 kilonewton, plus Rd going up. Okay, now we will know our Rd. When we solve this and substitute Rb to this part, then we'll know your Rb is, your Rd is 14 kilonewton. Okay, so you obtain your unknown. Okay, now you have identified the unknown forces. So now we are going to find shear force and also bending moment. Alright, so in order to do that, we have to split this beam into few sections. So as you know, previously in slide also you see that it advises you have to split it into few sections. So I'm going to split my beam diagram, my free body diagram, into 3 sections. This is my first section, this is my second section, and this is my final third section. Okay, so this is section 1, my section 2, and also section 3. Okay, section 1, section 2, and section 3. So now let's do the calculation for shear force at each section and also the bending moment for each section. Okay, right, so now let's do for let's find V1. So let's say I'm going to find the shear force for this section. So remember, so I'm going to cut it to this part. So you remember, if we cut the section to here, okay, we have 20 kilonewton. When we cut it like that, so we're going to have our V1 like this, our M1 like this. Okay, signage as you remember in your slide. So this will be your V1, M1. Okay, so I would like to find V1, shear force that is developed due to the load. Okay, so now I need to find the shear force and the bending moment which are developed because of the load at this point 1, at the section 1 of your beam. Okay, let's do this. So V1, how I'm going to do the calculation for V1 is minus 20 at point A, minus 20 going down, kilonewton, minus, because going down, V1 equivalent to 0. So you obtain your V1 equivalent to your V1 then minus 20 kilonewton. So your shear force for this section, just right before the next force, you cut it just before the next force. So the shear force here, because of this force, because of the load 20k at this point, just because of this 24 up to this point, just before the second force, your shear force which is developed here is negative 20 kilonewton. Okay, so now I would like to find the shear force for section 2. Okay, shear force at section 2. So V2 equivalent to minus 20 kilonewton. And then section 2 means all the whole thing plus, because we have RB going up. So what is our RB? 46. Because we cut it here. This is okay. This V2, M2 is going this positive, right? Okay. So positive. Okay, this is minus 20, and then you have something here 46. Okay, 46 minus, because going down, V2 equivalent to 0. So you have your V2 is 26 kilonewton. So you know here at this part your shear force is actually 26 kilonewton. After you at this part, at this section, your shear force is minus 20. And then when you go along the beam up to section 2, so this part, your shear force is 26 kilonewton, no longer negative 20, because you have actually, when you go up to this section, you have another force acting on your beam, external force acting on your beam. So your internal force, shear force here becomes 26 because of this additional force, external force. Okay, now let's find V3. V3 means 1, 2, 3 up to here. So in V3 we have minus 20k, plus this one, we have 20k going down, and then we have this is 46, and we have another force here, right? 40 kilonewton. 46 like that. Okay. So let's find V3 here. V3 is minus 20 kilonewton plus 46 going up kilonewton minus 40 kilonewton minus V3 equals to 0. So our V3 equivalent to our V3 is equivalent to minus 14 kilonewton. Okay. So this part, our V3 would be minus 14 kilonewton because we have another force acting here. So we have only 3 sections. We have only 3 segment of beam, 3 section of the beam that we have split just now. So we have only 3 shear force, 1, 2, 3, which we have already encountered. So now we have to find the moment of your bending moment that happens at this force, happens on this beam due to the external force or loading that we exert on the beam. Okay, so now let's find moment. So moment, for calculation of moment, we are going to use the area under the curve method. Okay, so area under the curve method. Okay, I'm going to write down the equation. Where is the equation? Yeah. Okay, so we are going to employ this equation to find moment, the bending moment. Okay. Let's see, x1, x0 equivalent to x1, x0, here would be 0, 1, v dx. So this we are going to employ this type of method to get moment of each section. So how are we going to do that? So to find that, okay, moment here is 0 because this force, a moment around this area is 0 because it has no distance, has no force, and it has no distance anywhere. Okay, so your moment at point O, moment 0 is equivalent to 0. So now let's find moment M1 for this section. At this point, moment is 0, but this section we have moment. We have a value for bending moment. We have value here and also value here due to the force that acting on each section. Okay, moment we established just now. Moment about this point is equal to 0. So let's find moment about this section. Okay, so we are going to use this equation. We want M1. I'm finding moment now. Bending moment at this section. M1 minus M0 equivalent to V1 dx. So you know this dx is the distance between 0 to 2.5. Okay, this M1 is actually area AB where is from 0 to 2.5 in terms of distance. Okay, section, right? So what we